Swayam Prabha. Digital India. Educated India.
Good morning, everybody. Today we will discuss heat transfer from a tapered fin. We have already discussed about various kinds of fins. Now, this particular fin is attached to the base body and it protrudes outside in the form of a tapered fin, and this is basically shape of the wedge. It is convenient to choose the origin of the coordinate system at the tip of the fin. We will see that is definitely having some advantage. If we choose the coordinate system at the tip. So x is in the direction towards the base, horizontal direction, and then b is the width of the fin, and twice w is the thickness of the fin at the body. Now, Sx is the surface area which varies with x, and we can very easily see that this can be calculated as twice b into this any one of the side of this triangle that is given by root over x square plus w square x square by L square. So if we take out x outside the root, we can write bx root over 1 minus w square by L square plus area of this triangle on both the sides, which is given by basically twice w by L x square. So that is the surface area. You can verify that again. We have to calculate these two side means half base into altitude, and two sides it will be added up, and top surface is b into root over this quantity, bottom surface again b into root over this quantity. So together we can write Sx is twice bx root over 1 by w square by L square plus twice w by L x square. And then ds dx divided by a, we have to find out the derivative of this quantity divided by a. A is the varying area of the fin, cross-sectional area. So this, which will be basically twice w bx by L. So we have found out the derivative of as and divided by a, which is basically this area. At the base it is twice w into b, but at different x it will be twice W B into x by L. So this is ds by dx divided by A. We can further express this as S prime by A, and we rationalize it little more. 1 by x L by W root over 1 plus W square by L square plus twice B, which can be approximated as when W is less than L, then this can be approximated as 1 by x L by W plus 2 by B. Similarly, we have said AX at any x, the cross-sectional area is given by twice W by L into x into B. And here also we can say dA dx divided by A equal to 1 by x. Now, why did we find out dA dx by A and ds dx by A? Because we have seen these are the parameters involved in the governing equation for the fin, general equation that we derived, which was d2t by dx2 dA by dx whole divided by A into dt dx minus h divided by Ka ds by dx into T minus T infinity. T infinity is the ambient temperature, H is the heat transfer coefficient, K is the thermal conductivity of the material, A is the cross-sectional area of heat transfer, and S is the surface area through which convective heat transfer takes place. H is the convective heat transfer coefficient. Now in the governing equation, we were to substitute dA by dx divided by A and ds by dx divided by A, these two parameters, that means this one and this one, exactly that we have done, and then we can write d2t dx2 1 by x dt dx minus h by k into 1 by x into L by W plus 2 by B into T minus T infinity equal to 0. The second term in the parenthesis is negligible compared to the first term. So we can neglect this term in the parenthesis, and equation reduces to d2t dx2 plus 1 by x dt dx minus h by k into L by W T minus T infinity into 1 by x equal to 0. Now, for a given condition or given fin that are given fin which are usually applicable or applied in several application purpose, we can look at the fin parameters, geometrical parameters, and we will find that this governing equation d2t by dx square plus 1 by x dt dx minus h by k into L by W T minus T infinity into 1 by x equal to 0, this is justified. Now, if we substitute theta equal to T minus T infinity, that means temperature, in excess over the ambient temperature. We can convert this equation into d2 theta dx2 plus 1 by x d theta dx minus 1 by x h by k L by W into theta equal to 0. And we can again take up or substitute a parameter, introduce rather a parameter rho given by beta into x power gamma, which will give us d rho dx equal to beta gamma x power gamma minus 1. Or we can write d theta dx equal to d theta d rho into d rho dx, which will give us beta into gamma x to the power gamma minus 1 d theta d rho. Then we find out double derivative d2 theta dx2, which is nothing but ddx of d theta dx, and again ddx of beta gamma x to the power gamma minus 1 d theta d eta. And first we club this together and find out the derivative multiplied by d theta d eta, and then we leave this and find out the derivative of d theta d eta, which is d2 theta d rho 2. So extremely sorry. Again, let me repeat. ddx of beta gamma x to the power gamma minus 1 d theta d rho. First, we find out the derivative of this part, beta gamma minus 1 x into gamma minus 2 into d theta d rho. Then we again find out the derivative of d theta d rho, and d theta d rho derivative is d2 theta d rho 2 multiplied by beta square gamma square x to the power twice gamma minus 2. So basically ddx of d theta d rho into b gamma x to the power gamma minus 1 will give this part. So now we can substitute the governing equation d2 theta dx2 as d2 theta d rho 2 beta square gamma square x to the power twice gamma minus 2, and we can find d theta dx containing d theta d rho, and d2 theta dx2 also will give us 1 d theta d rho. So if we collect these two terms containing d theta d rho, and remaining terms are 1 by x h by k L by W theta equal to 0. And then we perform little algebra, which will give us beta square gamma square x to the power twice gamma minus 2 d2 theta d rho 2 plus beta gamma square x to the power gamma minus 2 d theta d rho plus minus 1 by x into HL by KW theta equal to 0. And finally, again further reduction will give us beta square x to the power twice gamma d2 theta d rho 2 plus beta x to the power gamma d theta d rho minus x by gamma square HL by KW. H is heat transfer coefficient, K is the thermal conductivity, W is the width of the fin at the base, and L is the length, into theta equal to 0. Now what we do, we consider this, we took beta into x to the power gamma as rho. So this we can say rho square, and this is rho. So rho square is beta square x to the power twice gamma equal to x by gamma square h by L, which are the physical parameters associated with theta. If we do that and substitute gamma equal to half, we will get beta square equal to 4HL by KW, which will again give us beta equal to twice root over HL by KW, which are basically fin parameters. So the equation, we are, mathematical paradigm, we are describing in such a manner, or we are modeling in such a manner, so to say, that all the fin parameters are involved. So then we get beta square x to the power twice gamma d2 theta d rho 2 plus beta x to the power gamma d theta d rho minus x by gamma square HL by KW into theta equal to 0. Now this allows us to write, this is rho square, so rho square d2 theta d rho 2 plus rho d theta d rho plus this, now with gamma equal to half, this tantamounts to rho squared theta equal to 0. So we can write d2 theta d rho 2 plus 1 by rho d theta d rho minus theta equal to 0. Straightforward from this equation. Now this equation exactly fits in the expression for modified Bessel's equation. Now, since we have mentioned about modified Bessel's equation, so situation demands at least once we express what is Bessel's equation. Bessel's equation of order n is given by x square d2y dx2 plus x dy dx plus x square minus n square y equal to 0. Second order differential equation. Its solutions are Bessel's function of first kind of order n, because order of the equation is defined by this parameter n. So its solutions are Bessel's function of first kind of order n and Bessel's function of second kind of order n. And Bessel's function of first kind order n is given by Jnx equal to x by 2 to the power n summation over m equal to 0 to infinity minus 1 to the power n m factorial m into gamma m plus n plus 1, this is capital gamma, uppercase gamma, x by 2 to the power twice m. And similarly Bessel's functions of second kind of order n is given by ynx 2 by pi ln x by 2 plus this gamma doesn't have any link to our gamma, this is Euler's constant, into Jnx. Our gamma means the fin parameter. When we discussed, we substituted gamma equal to half. This is basically Euler's constant. This is not with to be equated with our physical problem. Minus 1 by pi, again summation m equal to 0 to n minus 1, n minus m minus 1 factorial divided by m factorial x by 2 to the power twice m minus m. So this is Bessel's function of first kind of order n, Bessel's function of second kind of order n, and usually solution of this equation is given by Bessel's function of first kind plus Bessel's function of second kind. And we are discussing equation that is identified with order n. If we substitute n equal to 0, in some physical problems we will find n is 0, then the solution will be, again, let me repeat, it is nth order equation, solutions are Bessel's function of first kind of order n, Bessel's function of second kind of order n, some constant into jnx plus another constant into ynx. Now, if the order of the equation becomes 0, then solution becomes Bessel's function of first kind of order 0. That means a j naught x plus b arbitrary constant y naught x. Y naught is a Bessel's function of second kind of order 0. And the Bessel functions, j naught and y naught, they vary with x in this manner. So this is just I mentioned about Bessel's function because we may come across Bessel's function in our subsequent lectures, but in this lecture it is not Bessel's function. We have come across modified Bessel's equation. So now come to modified Bessel's equation of order n. This is given by x square d2y dx2 plus x dy dx minus x square plus n square y equal to 0. So what is the difference? If you look at Bessel's equation, x square d2y dx2 plus x dy dx x square minus n square into y. And here what we are getting, x square d2y dx2 x dy dx minus x square plus n square into y. Here it was plus x square minus n square into y, which was Bessel's equation, and modified Bessel's equation minus x square plus n square into y. As such, in the Bessel's equation, if you substitute x by ix when I is imaginary, root over minus 1, you will get this equation. I'm not going into that detail, just let me continue with the modified Bessel's equation. Modified Bessel's functions of the first kind of order n and argument x denoted by inx, and modified Bessel's function of the second kind of order n and argument x denoted by knx are defined respectively by the infinite series. Inx is given by summation over m equal to 0 to infinity x by 2 to the power twice m plus n divided by factorial m into gamma, capital Gamma, m plus n plus 1. And knx is given by pi divided by twice sine n pi I minus nx minus inx when n is not equal to 0, 1, 2, or we can say knx equal to limit m tend towards n pi by twice sine n pi into I minus mx minus imx for n equal to 1, 0, 1, 2, etc. Now Inx and Knx are real and positive when n is greater than -1 and x is greater than 0. And you know all these Bessel's functions and modified Bessel's function, they have numerous recurrence relationships which can be found out from their derivative, from their integration, and involving modified. Now among a host of recurrence relationship, we are mentioning few here. Inx is minus I to the power n into jnx. Inx I minus nx equal to I to the power minus n j minus n, and argument is ix. Actually, derivative of Inx is given by these expressions: I n minus 1x minus n by x Inx equal to n by x Inx plus I n plus 1x. And when n is 0, we can plot I0x as this and I1x as this. I1x is the derivative of I0x. And these are the relationship with the, you can see Jnx and Inx, and relationship between In and Jn. Few other recurrence relationship, that is derivative ddx of x to the power n Inx is x to the power n I n minus 1x. ddx of x to the power minus n Inx equal to x to the power minus n In plus 1x. So if you substitute n equal to 0, we can get basically derivative of I0x as I1x. And I0x and I1x can be plotted with x. In this way, it will vary. Similarly, knx can be 0, 1, 2 of order can be varied, and for n equal to 0, we'll if we plot, the variation will be some such variation, and its derivative k1's variation will be again some such variation. From x equal to 0, we can see k0 is infinity. So let us come back. If n equal to 0, we get modified Bessel's equation of order 0. So x square d2y dx2 x dy dx minus x square y equal to 0. We can further simplify it. d2y dx2 plus 1 by x dy dx minus y equal to 0. And the solutions are I0x or I0x equal to summation over m equal to 0 to infinity, x by 2 to the power twice m factorial gamma m plus 1. This gamma is basically gamma function, right? Uppercase gamma function. You may recall the beta and gamma functions. So this is gamma function. And this is k0 x. So our equation was del 2 theta del rho 2 plus 1 by rho del theta, sorry, it is not del d2 theta, it is not partial derivative, because it's a function of rho only. So d2 theta d rho 2 plus 1 by rho d theta d rho minus theta equal to 0. So exactly matching with the modified Bessel's equation of order 0. So solution is theta equal to C1 I0 rho plus C2 K0 rho. And what is rho? Rho is beta root over x. we have seen, we have substituted already. So which became, if we recall, we took rho equal to beta square x to the power twice gamma, and we have substituted gamma equal to half, so it is beta square x, rho equal to, rho square equal to, and rho equal to beta root over x. So C1 I naught beta root over x plus C2 k naught beta root over x. At x equal to 0, I naught equal to 1. This is basically the way we can see if we plot I naught equal to 1 at x equal to 0. So at x equal to 0, I naught equal to 1, but k naught tends towards infinity. Now this will demand to have if when we at x equal to 0, if this tends to infinity, solution has no meaning. So k naught, that demands k naught, since it is tending towards infinity, C2 has to be 0. So C2 is 0. So theta equal to C1 I naught beta root over x. At x equal to L, that means at the base of the fin, theta equal to theta naught. We have taken x starting from the tip and going to negative x direction, ending at x equal to L. So x equal to L, theta equal to theta naught. So we can write then from here, this is not there. So theta naught x equal to L equal to C1 I naught beta into root over L. So theta naught equal to C1 I naught beta into root over L. So from where C1 is basically theta naught divided by I naught beta into root over L. So we get our solution since C2 has been evaluated, C1 has been evaluated, C2 is 0. C1 is theta naught divided by I naught beta into root L. So theta equal to, general solution, theta naught into I naught beta into root x divided by I naught beta into root over L. So if we can look into this modified Bessel's function and a Bessel's equation or equation matched with modified Bessel's equation of order 0, then we found out our solution as combination of modified Bessel's function of order 0 of first kind and modified Bessel's function of second kind of order 0, and the k naught second kind at x equal to 0 infinity, that is why C2 became 0. C1 became basically theta naught divided by I naught into, argument was beta root L, and from there we have found out the general solution, theta equal to theta naught I naught beta root x divided by I naught beta root L. And if we find out its derivative, d theta dx equal to beta x to the power minus half by 2 theta naught into I1 beta root x into divided by I naught beta root L. So derivative of I naught we get, I mentioned it earlier, we get from the recurrence relationship, and it becomes I1, and we get basically theta naught I1 beta into root x divided by I naught beta into root L, and if we differentiate the argument we get beta x to the power minus half by 2. So the heat transfer at the base then given by, it will not be minus Ka d theta dx because coordinate system is in the negative direction. It will be plus Ka d theta dx at x equal to L. So then we keep on substituting. This is K. At the base area is twice W into B. And then d theta dx, we have already found out d theta dx. And in this expression, we substitute x equal to L. So beta L to the power minus half by 2 I1 beta root over L divided by I naught beta root over L. So here we do little more algebra. Q equal to K twice WB into 2 into root over. We write the expression for beta also. HL divided by K into W into L power half minus half divided by 2 theta naught I1 beta root L divided by I naught beta root L. So finally we get heat transfer rate as twice theta naught into B. B is the width of the fin, root over HKW. H is the heat transfer coefficient, K is the thermal conductivity, W is the width of the fin at the fin base, I1 beta root over L divided by I naught beta root over L, where beta root over L is given by twice L root over H by KW. These are all fin parameters. So if we can determine the value of I1 and I naught with the respective arguments, we will be able to find out the heat transfer rate. And units are properly taken care of. These I1, I naught, these are available modified Bessel function table. I have given some example table. If this is the argument, this is the modified Bessel function. These are the argument, these are the modified Bessel function. So these tables are mathematical tables are available. You can use, if you know Mathematica also, for a given fin. After having chosen beta and L, you can easily find out. If you know H, if you know KL, you can find out. If you know the temperature difference, you can find out heat transfer rate. So we will stop here today. Thank you very much for your interest. Thank you.